of the lecture of yesterday that I couldn't finish. Right. So, given the question that you asked yesterday, I only added a couple of extra slides. There you are. So, what's your name, by the way? Bernardo. Okay. So, yesterday I forgot to include this plot that is very important because it's the radius versus mass of the planet. And it's the first evidence of characterization that we have for exoplanets. So you measure the radio through the transit method, and then combining it with the radial velocity, which is the spectral observation. So radius is photometry, and then radial velocity is with a spectrum. Then you can resolve the mass. And so what you do, basically you combine them in these plots, and then you see that you have all of our exoplanets that are with their specific error bars. But that gives you already a hint of the bulk composition of the exoplanet. So you see in the different models, this is, for instance, like, obviously you have the radius, you have the mass, you have the inner density. That's the trick, right? So, which is the first taxonomic classification of planet. So here you have the model of if an exoplanet was done 100% made of iron, and then here would be like 33% made of iron, and then you see that there is a bump of exoplanets that are fitting with this model, and so on and so on. So if we only have radius and mass, this is the way we say, like, okay, so this exoplanet is we expect it to be a water world or a rocky world or the different classes of exoplanets. So here you have 100% of water. This is, of course, just for Earth masses, but obviously, like, if you go further to the right, you have also like the giant gas giant population, which will fit models of hydrogen-made exoplanet and so on. Here you have the metals because we are talking, this is the sample of rocky exoplanets. And you have, okay, yeah, up here already like Uranus and Neptunus and so on. Okay, so that was an extra thing that I forgot to mention yesterday. It's very important. Obviously, to know the composition of an exoplanet, to really know how it is made, you cannot use just this, because obviously you have error bars. So what you really need to do is to do the characterization of the atmosphere of these exoplanets, and you do that by doing basically a transit as a function of your wavelength for a large wavelength band. So you extract the planetary spectrum, okay? And this is what the aerial mission will do. The aerial mission is a space mission, an M-class mission by the ESA, and it's going to be flying in 2028, 1 year after 2029, 1 year and a half after Plato is launched. And it's dedicated to study the atmosphere of 1,000 exoplanets, because the final goal is indeed to do a planetary population study, not just understanding, one specific planet, but to understand more of the formation and evolution of exoplanets. You can do that only if you know the atmosphere and you have a data and a population that is collected and interpreted in an homogeneous way. Okay. So the other update was this one, because it really pissed me off not having to show finally the light curve. So when you have the first planet that is just crossing along the stellar path, you have the depth. But then in the moment you have a second one that is crossing, okay, you have a second transitory depth, but then you have a third one. So it's like basically summing up the signal. So what you do to understand that you're detecting a multiplanetary system or other bodies, you need to combine your signal. So you need to model your light curve, and what you do, you have your data that is weird, and then you model your light curve, you fit the data, and then you observe the residuals. And then if you see that there's still some structure in the residuals, you keep changing your model until the residuals are like really, really flat. And then you might, so what you do basically, you keep adding bodies. Okay, so there's this teeny tiny bump extra, so this is a sum of 2 planets, okay, let me add an extra planet, and so on. So you do this game of changing and trying to fit as best your data. The other update, and thanks Christina that we discussed that after the lecture yesterday. Yesterday I said that there was no exoplanet that was detected by astrometry, which is still correct, but it's not completely correct. We have 3 exoplanets that were detected by Gaia. They were not detected through astrometry, but they were candidates. So the first 2 were like Gaia 1b and 2b, and it was confirmed it was a transit detection. So here you have the 3 different bands of Gaia, so the G band, the GBP, and the GRP. And basically what you see, it's actually detecting the transit. So this was a detection by Gaia, an astrometry observatory, but it was through photometry, through transit. And then the third planet is this one, which was a candidate, and it was confirmed by radial velocity from the ground. So just to be, it's a classical example, no? Someone believes something, and then you discuss with your colleague, and it's just, yeah, I didn't check that. Let me go and check that, and then it's really good. It's like, so you keep updating your own knowledge, right? And these were the updates. But now I'm going to carry on about telling you about the long-term evolution of circumbinary planets. So just to recap, you remember that I said planets can survive the evolution of the star. It can happen in the single star case, but it's more likely to happen in the binary case, because close binary case, because the stars are evolving together. Basically, they keep each other at bay, so no one is expanding too much and destroying all the planetary system. So that's the idea. But let's see, indeed, what we know on the theoretical level. Back in the time, in 2016, we only had, I think, 9 planetary systems, circumbinary planetary systems detected by Kepler. And Veselin, Kostov, he did this very nice simulation that took this planetary system, and then it evolved, I think it was 9, yeah. It evolved the stars to see what was happening to the planets that were bound to the star. Many things happen, of course, depending by the type of, he used specifically the alpha formalism, you can check here. So this was for the case of 0.2 and then 1. So you have two different options. And for the system 1647, and here it was for alpha 3, 5, and 9. So he tried to understand what was happening to the planets depending by the type of evolution the binary was having. Like you can see, this is the primary RLOF, which is Roche-Loeb overflow. So that's one other acronym that we use a lot. And the Roche-Loeb overflow is when one of the massive stars, the first massive, because this is the primary, the giant star is fill up the Roche-Loeb, and it's starting the overflow towards the secondary star, okay? So he used the stellar evolution code and n-body code, and then he found that in some scenarios, planets were ejected, some other was were destroyed, and some others, in one case, specific case, there was one planet that was surviving the 2 common envelope phases of the system. So he was the first one that indeed proved that planets are more likely to survive around binary stars instead of single star. The second work was done by Gabriele. He was a student of mine and at the master level, Now he's doing his PhD in Padova, but we decided to take the work by Veselin on a population level. So what we did, we used a triple evolution simulation code that was done for stellar triples, and we adapted it to the planetary processes, because it was not made for planets, it was made for hierarchical system where you had 3 stars, not 2 stars and 1 planet. So we ran 2 different populations of 10,500 planetary system to try to find a trend to what was happening to these exoplanets. So these are just the feature. I'm not going to go into detail, but these are the features that we included. So for the planets, of course, so this was the stability orbital criterion that I mentioned yesterday. Then we had also the planetary rotation velocity, because it's different for the star. The photoevaporation by the irradiation of the star, because I mentioned the white dwarf, when they become white dwarfs, they're very hot. So at 30,000 Kelvin, the radiation is very strong. So what's going to happen to the atmosphere of my exoplanet in that case, right? So, oh yeah, and this is the mass-radius relationship that I was mentioning yesterday. That is like Cannon keeping. Because sometimes you don't have, well, we needed to know the radius as a function of the mass and stuff. Okay. So when you do this kind of population synthesis, you might be lucky and know all of your priors, but you might also not be lucky and not knowing what is the real distribution of these bodies. And this is indeed the case for circumbinary exoplanets, because you saw it yesterday. We found 25. How can you find the statistics of the mass distribution, of the separation distribution? It's quite tricky, right? So the approach that we used, well, for the inner binaries, we only had 1 distribution, and this is the distribution that is well, for mass 1, mass 2, and separation eccentricity. This is the distribution that is best matching the observational data that we know about at the moment for double white dwarfs. And it's also the distribution that was used to produce the LISA double white dwarfs population. So it's, yeah, so this one, we only had 1 option. For the planets, so we had population A, where we combined by what we had, the distribution that we could see for single star planets. So just assuming that the circumbinary distribution will be similar to the single star planet. So we had a uniform distribution for the mass of the planet, and a log uniform for the separation from the inner binary, and then the eccentricity was a beta function. And all of this was found in the literature. But then you have to be conservative. It's like, okay, this might be what we have, but what if not? So you just assume like a flat distribution. So we had a second population made just of uniform distributions, as in we know nothing. Let's see what is coming out of it. And here it comes with the Magrathea population. Who of you has read the Hitchhiker's Guide to the Galaxy? Which in Portuguese will be? Guia das Mochilas? Ah, mochileiro, tá bom. Parece, né? So, we decided to call every planet that is orbiting a double white dwarf a Magrathea planet, because in the book, at some point, there's this description that there's the Magrathea planet that is like orbiting 2 white suns. So obviously, I just think like, oh, 2 white suns, it's definitely like 2 white dwarfs. So I really hope that this term is already catching like on people, because we published 3 or 4 papers with the name Magrathea, and now I have a new NASA collaboration that they are just talking like, oh yeah, but like how do we detect Magrathea? And I'm like, yes. So excited. But yeah, it's Douglas Adams, the author of this. But anyway. Okay, so we want to know how many planets around double white dwarfs we have. so how many Magrathea planets we have, because those are the planets that LISA might be able to detect. So we highlighted the Magrathea planet for population A, population B, and then obviously we have all other set of stuff that were happening. So Magrathea was surviving the devolution of both of the stars. Then we had a percentage of collided exoplanet destabilized, as in the planetary system got destabilized and the planets were ejected. Well, the planet, because we only simulated for one planet. It's not multiplanetary system. That's another thing. Merged where the binary merged, and then, yeah, we had stuff that was not evolving because it was taking ages, and I don't remember what was stable empty. Okay, but the important message here is that, like, I remember when I applied for a grant back in the past, and I was like, no, I want to study this. It was an European grant, and I really want to do that, and I think it's really important. And then one of the referees came back to me and said, like, oh, these things are rare. They will never happen. And then we actually found that 23% to 32% as a fun, well, it depends by the type of the priors you had, of planets really were surviving. So there's a high chance. I consider this high. I mean, for you, it might be low, but for me, it's high chance that indeed Magrathea can exist, right? Then if we detect it, it's another story, but like there's indeed a high chance. So these are the posterior distribution of population A and population B. What I wanted to highlight in here, so you have the planetary separation here, the eccentricity of both stars and planets. So planets is green and stars are yellow. This is the inner eccentricity, no, the separation of the inner binary, and then the mass of star 1 and star 2. So the way you have to read it is basically the injected distribution of when we injected the planets in around the main sequence stars. It's the dashed one. So in here you have, that's initial distribution of our planets was following this, of the Magrathea, they was following this part. And then you see that at the end of it, like a lot of planets got further out in your, in very much separated from the star. And that happened for population A and population B. So this is an effect of the evolution. So the stellar wind, and automatically the planets are, if the stellar wind is adiabatic, the planets expand towards the outskirts. The other important thing, it was eccentricity here. So we had, just pay attention, the yellow one for the star, we had the injection, or the eccentricity was basically flat for the stars. And then in the end, you see that you have this huge peak at 0, and then you have, well, other distribution that goes up to 0.6. But it's more or less what we see here. The peak at 0 is because, indeed, for the evolution of the binary and the production of gravitational wave, you have that your stars tend to circularize the binary itself. Ideally, if they don't circularize, it's because of the effect of the third body or other bodies that are like around it. Okay. So yeah, these are what I wanted to show you from here. I don't know if I included the one destroyed after, but just notice here, yes, I should be this. So we found out that the planets that survive are around the stars that have a maximum mass of 5 solar masses. If they have larger masses, the planet doesn't survive. So, oh, there it is. Yeah, I added it. Okay. So here it was the case of the collided or the merged. So exactly the same plots, more or less. But obviously the statistics is a bit lower. So yeah, for example, like just look at the. Wait, I'm getting confused. Okay, collided. So yes, indeed, collided. So this was the planetary initial distribution for the eccentricity. And look at the final ones, like they're all above like 0.6 because they got like in a very eccentric orbit, and then automatically it got to crash against the inner binary. So that was like dead. Or what was inner separation? Yeah, or indeed like the merged. You see here that compared to what we had before, that the masses were like injected in here, and then you had the peak of the retrieved at 0.1, and the same here. When you injected, like in this case, basically they merge straight away when you have higher masses. They merge straight away the two binaries. So in that point, we just stopped the simulation. Okay. So what we also found that it was interesting is that Magrathea prefer to have they have like, so again, these are the two injected ones. So, well, the destroyed, and then the blue one is Magrathea, and then this is what the inclination they had at the end of when they became Magrathea, indeed. And then you see that there is a peak around the 65. So we saw that even if we were injected a uniform distribution, by the end of it, like most of the system were peaking around the 65 degree with the plane of the inner binary. The goal is to do many more other simulations with a larger population, but of course it's really time consuming. So we just set down to 10,500. With the new server, like we'll be able to do more. But also, again, like so many things happen in the life of a binary. So we tried to see whether when the planet was destroyed, like, or the planetary system was destroyed, when this was happening. So we differentiate in the three phases. So you had the main sequence, and then you have primary star that is yellow, and secondary star that is green. And post-main sequence, and then in the white dwarf case. So most of the, apart from the merge thing that was happening just after the post-main sequence, most of the other destruction, let's say, happened in the main sequence phase. So like this is the count of the system that got when something happened during the main sequence stage. So what we are finding from this is like if they survive the main sequence phase, there will be a higher chance for them to become Magrathea. So yes, so some planets do, depending by the initial mass and separation from the central star. And indeed, they have more chances to survive there. Just a tiny point on evaporation, because this is very important given that we are dealing, yes? Yeah. No, I said that. No, I said that observational evidence is saying that is finding that all of the circumbinary planets have the same orbit as they are coplanar with the binary. But then I'm saying that is an effect of bias, like observational bias, because you detect them through transit, and automatically, if they are coplanar, it's easier to find them. What I said, it was if they have an inclined orbit at the beginning, it means that the frequency of circumbinary exoplanet is much higher than the frequency of single star exoplanet. But it's not, so here you say like we injected an isotropic distribution as well, like it was uniform all over the angles. So no, the initial inclination is not a matter of, it could be actually interesting to test indeed. Yes, yes. So you can see it already here that it's changing and going towards the lower than 90 degrees, for instance. But it's actually interesting. I never thought of like just setting like polar planets and see what's happening in this type of simulation. I'll think about it. Okay, so coming back to evaporation, as I said, the white dwarf goes extremely hot. So it can indeed like evaporate percentage of the atmosphere of the exoplanet. For our simulation, we saw that it was a very, very tiny percentage, just like 1% or even less. So it was not really relevant as we thought. In any case, it's a danger. For us, it was not, because it was a circumbinary, so it was already like further away than the usual single-star planet. In general, and this is valid for both circumbinary and single-star case, the high luminosity will indeed affect the exoplanet and partially evaporate it or change the chemistry sometimes as well. And the terrestrial planet can be completely evaporated, and for such like Chow habitability options. And then yes, exactly. This was like extracted from a paper of Veras and Vidotto. There was just some consideration about the habitability of the planet, of course, which can cause heating for the surface, of increased irradiation and loss of planetary magnetosphere, and so on and so on. So I don't want to go into detail, just to let you know that sometimes it can really affect and change the planet. Right, so also this was an extra thing. Remember the planetary nebula when the planet is evolving and then is ejecting the envelope, right? The star is evolving, ejecting the envelope, sorry. So it was fun because I found like these papers from, well, this paper, they said that the shape of the planetary nebula can also be caused be due to the presence of planets that are interacting with the stellar wind that is like ejected from the star. So that was just an extra thing I wanted to mention. Okay, there's another option that I didn't include in the single star and binary star case. We also have a planet that can survive the common envelope, such as we have a body, a smaller body around a single star, and then again the star is evolving and it merges with the star, and then you might have the formation of a new protoplanetary disk from which you form a new planet, or even you could have something that is like just surviving the evolution, and then you have it that is coming out of the envelope. Obviously, it's a rarer option. But this could be the pathway formation of one of the exoplanets that was found by transit, which is WD 1856b, that it was just at 0.02 AU from the star. It's a single star, so very close by. Obviously, there are a lot of interpretations, but this is one of the suggestions of survival. Sometimes it might have been even like a larger body. It could have been like a brown dwarf before, and then they got on common envelope phase, and then a smaller body, such as a planet, gas giant planet, came out of the common envelope. Do you see that happening? It's just like sharing a bit of atmosphere, and then like when the main star is reducing, the secondary object will survive, but like stripped of some of the mass that he had originally, and then the mass is going to be slower, and then it's changing the nature of its own body. Yeah, okay. Okay, so just to do a recap of survival option. You can have the planet survive because they are outside the common envelope, and in that case, the interaction with the star are less than single star case. Then I included that we detected planets around a single star white dwarf, which is Blackman microlensing. Gansinke, it was a spectra thing, but this is a giant exoplanet that is evaporating. They didn't see the planet, but it's the best interpretation of the data they collected. And then Vandenberg, that it was by transit. And then there's Chu, 2021, which they basically found that there is a white dwarf that is eating. It's very hot. It's like, this is the temperature, that is literally eating the atmosphere of the gas giant because of the gravitational pull. The option, okay, the planets can survive because they are outside the tidal engulfment radius, so further away. They can survive the common emperor with a single star. Of course, they are more massive, and it's going to be easier to survive. But also, you need to consider that planets around single white dwarf could be just a result of a planet that survived the merging of two white dwarfs. So two white dwarfs are merging. They don't pass the 1.4 solar masses limit, and then you have just one white dwarf and the planet. Oh, yeah, okay. And this is the one that I added after your question yesterday. So there is a circumbinary system where we have a pulsar and a white dwarf and an exoplanet. But they found out that it was not originally, it didn't evolve to be that kind of a planetary system. It evolved because of a capture of another star. So we had the original system, main sequence with the planet, and then at some point this planetary system crossed through the core of a globular cluster M4. At that point, there was another star that was passing by. There was a neutron star and a companion. So what happened is that our initial planetary systems got captured the neutron star, and the companion was ejected. And then the main sequence star evolved and became a white dwarf. So basically, you have the neutron star and the white dwarfs are combined together, and then you have the exoplanets around. So that's one other option. But it's because of dynamical encounters, not because of the singular evolution. Well, the binary evolution. OK. So very quickly, take-home points, and then we go to the LISA thing. Yeah, well, I guess you know now what are exoplanets, right? OK, the circumbinary planets form far away and then migrate inwards. They have higher chances to survive. The tidal radius is really something important to consider for the survival. We can have quite few migratory exoplanets, but the final thing is like we really need more observation. One, to know the priors of our distribution to do a more focused simulation, synthetic population simulation, or also, yeah, exactly. That's what I said. Yeah. Any questions before we move on to the next similar topic? I promise I'll try to keep you awake. I'll do my best. OK, detecting planet with gravitational wave astronomy. Yay! Through the LISA mission. Yay! OK, so I have the first 3-4 slides made by, I took it from a talk that was done by Nora Lutzengendorf in the LISA symposium that was just July, like a couple of weeks ago, to just introduce you to the topic. So gravitational waves are real, hopefully. Okay. They was like first theorized by Einstein in 1988. And then, well, I think some of you are more expert than me on the case, but right, this was the first, what was this again? You are the gravitational wave people, right? So what was this? You don't remember? Do you know? I don't know, because I don't, okay, fine, let's just skip this. So it was first theorized by Einstein here, and then this was like the first, let's say, evidence that they could actually exist. So we had by Taylor and Hulse, they had a perfect fit to the data. So the data.
You mean until 57 people worked it out and it was a gauge artifact, or if they were actually carrying physical momentum and physical angular momentum?
Yeah.
Until 57 people didn't know.
Ah, okay.
Actually, some people knew, but they didn't convince the whole community. I mean, Weil already wrote it in the 20s, but apparently he never fully accepted this one.
Okay, so basically he theorized it first, and then in here they were like trying to convince people that they were actually existing.
Yeah, they were physical and not a gauge artifact. I mean,
okay.
you can have many solutions that are not physical in general, but there is a parameter.
Do you want the microphone? Because this is very interesting. Because obviously it's like there are things that I don't know.
Yeah, if you follow those who follow my general report, they don't.
I didn't turn it on.
The microphone is off.
Yeah.
Basically, at the time of Einstein, the Weil already wrote that there are many polarization in the metric tensor, and only two of them propagate with the speed of light. And mockingly, Weil said the others propagate with the speed of thoughts, in the sense you can give them any speed you want. So Weil understood it in the 20s, but somehow he didn't manage to convince the community. So in 57, there were several independent work, including Feynman, that convinced other people that, yes, they carry energy. Basically, the famous argument that went through the history was the argument by Feynman. He said, look, if I have two test masses and the gravitational wave passes, they will start oscillating and they will go at rest. But they will not gain any energy, okay, because they are in free fall. But if I put a spring in between them, they will not oscillate exactly in phase, just because they are different places in the space. So by not oscillating in phase, the spring will have a differential motion, will compress and stretch. So if the spring has no friction, again, there's no net transfer of energy. But if the spring has friction, will heat up. So if the gravitational wave can heat up a spring, then it must carry energy. Basically, this was the argument by which he convinced the people. By the way, there is a funny story that he wrote back to his wife while he was at the conference and said,
to his wife?
Feynman wrote back to his wife. He had many, but to the wife he had at the moment.
Okay.
Said, sorry?
His
it was
friend,
not a wife, it was girlfriend. Said, okay, these people don't understand anything. Next time that I tell you I'm going to a general relativity conference, tell me not to go.
For real?
Yes. But then after that, basically started the experimental search for gravity. Since the community was convinced that gravitational waves carry momentum, energy, and angular momentum, then in principle you can detect them. But until then, the community was not convinced. So in the 60s, the experimental search of gravitational waves actually started. And as you said, 74, the start of Hulse-Taylor monitoring that took many years was, the proof that everybody agreed upon that, yes, they carry energy momentum because they are making at least one system decay. So,
thank you so much, because I read about it, but like I couldn't. No, okay, yeah, I couldn't explain it in detail. Okay, so then in 2016, we had the first detection by LIGO Virgo. And 2023, we had another detection of the evidence of the pulsar timing array gravitational wave by ground. So what I wanted to highlight, by the way, the talk, you can have a look at the talk. It's on YouTube. You just put this on YouTube, and you have the whole talk if you are interested. What I wanted to highlight in here is the fact that LIGO and Virgo cover very low frequencies, and then like we have like low frequencies here, and high frequencies there. No, the opposite. Yes. 10 to the minus 9, 10 to the minus 9. Yeah, sorry. And then there's a hole in the middle for which we have to have LISA to cover that. So we go to space and we build LISA, because otherwise that was not, it was not covered. Okay, so very quickly. It was an idea by Bender in 1974, and then it was suggested again for antenna for laser gravitational wave observation in space, million of kilometers of size antenna in 89. Obviously, it was not accepted. So in 1993, they proposed it as an M3 mission, and that was like how it was looked like. If something is not correct, just let me know if you know about this. Okay, good, right. And then we had a moment of nothing that happened until they launched, like in 2015, ELISA Pathfinder, which was a mission very successful, for which they convinced ESA to have like a larger mission. So this was like one way of doing. So it was in 2017, given the results that they obtained from the Pathfinder, they proposed mission 2017, and then in 2024, it was officially accepted by the European Space Agency, together with collaboration from the NASA Space Agency as well. Okay, so the science objective, study the formation and evolution of compact binary stars, trace the origin, growth, and merger histories of a massive black hole across cosmic epochs, prove the property and immediate environments of black holes in the local universe using extreme mass ratio in spiral and intermediate mass ratio in spirals, understand the astrophysics of stellar mass black holes, explore the fundamental nature of gravity, prove the rate of expansion of the universe, and understand the stochastic gravitational wave background and their implication for the early universe. And the eighth one is the funkiest one, because it's about the unforeseen sources. So maybe the observatory will give will show something that we don't know about. Unknown, indeed. So this is indeed to give you the idea of where LISA is going to work and in which frequency range. So LISA here, and then we have LIGO and Einstein telescope, and then IPT and SCA there. Okay, so it's now a large mission because it's a lot of money and it's a very, very huge program. It's basically 3 spacecraft that are orbiting the sun in a triangular configuration. They are just behind, they are trailing Earth, so it's in the orbit like behind Earth. The arm length between the spacecraft is 2.5 kilometers, and the mission duration goes nominal mission will be 4 years, and then the extended mission until 10 years. And the idea is to launch it in officially 2037, but it could change. Okay, so as I said, it was LISA goes to fill up indeed that hole of frequency that was not covered from Earth. And in that case, it's very interesting because you are going to see a frequency range where we had many more sources, not just black holes. So we can see massive black holes, galactic binaries, extreme radiation spirals, and so on. But what I wanted you to pay attention is indeed like this bulk of galactic binaries, which are the ones that are interested for a Magrathea project. Indeed, the mission can detect tens of thousands of double-wide dwarf binaries all over the Milky Way, and this is the distribution all over the Milky Way. And I'm saying beyond because not just, we can observe also in other satellite galaxies, such the Magellanic Clouds and also Andromeda. Again, this was just like a zoom in where you have the LISA noise curve and sensitivity curve, above which we can indeed detect sources. And here you have what we expect to detect, all of the dots, and then indeed the verification binaries. So the verification binaries, they will be really important when you turn on LISA, because then we have to go and check that the calibration is okay, and then we can detect indeed the gravitational wave of this object that we already know they are existing. Cataclysmic variables. Yeah. So this is the population of double white dwarfs that we are going to detect. Well, it's simulated, right? So evolution of the galaxy and so on, evolution of binaries. It's a very elaborated simulation. But basically, you see that the bulk of the population will be of a chirp mass that is around 0.25. And here you have the distance from Earth. So the bulk of the population is around 8 kiloparsec, which is the distance from us to the center of the galaxy. And so, of course, like many more of them will be detected at that distance. But if we are closer to us, at lower distances, obviously the magnitude, the magnitude can also be lower, because this is G Sloan magnitude. The other thing is that for them to be detected by LISA, they obviously need to have a specific frequency. And so they have to rotate with a period that is between 3 minutes and 30 minutes. A double white dwarf is rotating with very fast, right? Yeah, but why indeed? Yeah, well, I'll carry on that after. Just to remind you again, like the size of a white dwarf, and also the other things that are important, like they are low mass stars because their progenitors are like less than 8 solar masses. They are faint. They are cooling down, so they start very hot and then they cool down. And then they are photometrically stable, and they are natural clock. The most important thing is like we have many of them because 90% of the stars will become white dwarfs. But yeah, so if I have just two bodies that are producing a gravitational wave, I will have like a monochromatic signal, so as a sinusoidal, a periodical signal for LISA. So LISA is able to detect things that are not merging also. And that was not the case for LIGO and Virgo, that indeed you could see indeed different frequencies where you see the merging of the bodies. But indeed, like if I have the center of mass of the binaries moving, I will have another effect that I will add. So basically, the gravitational wave signal that you're seeing is different from it's different from what the gravitational that they are, the signal that you're receiving is different from the gravitational wave that they are emitting. But I have a slide on that. So obviously, if I have a movement of the center of mass, it can be caused by different things. It can be caused by a presence of a planet around the double white dwarf. But it could also be a case of a binary black hole in close orbit around a massive black hole or a supermassive black hole. So the concept is worth in both of the cases. Right. I will focus now just on the planet case, for which indeed, if you have a third body that is like orbiting around a binary, you will have that the center of mass of the binary will move in a Keplerian orbit. So exactly, this is the effect that I was mentioning before. The binary itself would move with this frequency of the gravitational wave as a function of time. But then you have to account for the movement of the center of mass, which is this. And so you have that this is what you are observing, that is what LISA is going to observe, okay? So why did I say that the binaries need to have a period between 3 and 30 minutes? Is because this is the range of frequency of LISA. Basically, the two stars they are compact, so they are producing gravitational waves. And at the same time, like their orbit is low. They are slowly shrinking, and by slowly shrinking, they are producing gravitational wave. That's the case. But it's a low gravitational wave energy, and for such, we can assume it that is monochromatic, and then that it's constant. Basically, what I'm saying is like the frequency, like the gravitational wave frequency is going to change on timescales that are much larger than the observational timescales of LISA. So we can assume that they are constant. And see, so this is the formula of the center of mass, where k is like the k in exoplanets, so it is the semi-amplitude of the signal. And this is the inclination of the orbit and the mass of the binary. In simple words, it's basically, you can compare it to the radio FM, where you have a carrier, which is your gravitational wave, produced by your binary. And then you have an extra object that is like perturbing the orbit. And what it's doing, you're basically combining, and you have a modulated result, which is this. You can see that the result still, like the modulation is still periodical, and that tells us that there is something that is orbiting around the binary. And this is what LISA will be able to detect. By observing this, we are able to extract the period of the third body. It can be a planet, but it can be also a brown dwarf. The orbital phase, the parameter k, and it could be the eccentricity. This is a work in progress. We included in the last simulations, but it's still uncertainty, because the posteriors are very, very rough, let's say. Okay, but where can we detect these exoplanets or third body around double white dwarf? So this is the distribution of where we will have the double white dwarfs detected in the galaxy. So here is the sun, or LISA, both cases. This is our galaxy seen from above. So that's why you see a spherical thing, and this is like a cross-section on the other side. So this is still the center of the galaxy, and then you have a peak in here of detection for double white dwarfs. And just have a look at the signal to noise. There is a lower limit of 7. We need a signal to noise to 7 to detect the double white dwarf.
Here you're just comparing the monochromatic signal of each source to the LISA noise curve, are you?
There's a cutoff. I have the plots after. There's a cutoff of signal to noise of 7, which is the minimum. It's above the sensitivity curve. Because you have to do an average in the sky, and you have to do an average of the inclination also of the binary, because if it's in a specific inclination, you have less signal to noise because of where the gravitational wave is going.
But is this what people call confusion noise, or these are real signals that you can pinpoint individually?
These are real signals that you can pinpoint individually. So this was the outcome of a simulation of a binary population simulation. And then they took every binary at the end of the simulation, the double white dwarfs, and then depending by their mass ratio, depending by the distance from Earth, depending by the separation, they produce the signal to noise as a function of the location as well, of course, because it's the distance from Earth.
I'm a little confused, like, so these sources produce this monochromatic signal deep into the inspiral phase of the coalescence. And so, like, LISA will be hearing these signals, like, from multiple sources at the same time, right? Like, can you resolve them individually, or is more that, like, or is the signal more of like a background?
Okay, so just to clarify, these are just double white dwarfs. There's no third object in here, in this plot. So this is just to give you a context of where we can find, we can inject planets there to see where we retrieve them. So these are just double white dwarfs. That's the big, the holy grail of the LISA. Your question is the holy grail of LISA, because you turn on the microphone, because LISA indeed is a microphone, and you have noise from all of the sources all together. So what they are developing under different teams is called the global fit pipeline, which is fitting simultaneously all of the different sources. It's not easy, as you might understand, and I think there are 4 teams that are working on that at least. and they are developing indeed pipeline to account for signals from every kind of sources, right? For instance, after this work we did with the exoplanet, Michael Katz, that is one of the guys that is developing the global fit, included like a third body detection inside the global fit, because before it was not accounted for. But then we saw that it's important to account it for. It's, if you ask me details about how it works, I cannot answer that because it's very complicated. But the idea is that everything is fitted simultaneously. Obviously, you will start with the things that are clearly have a high signal, and then automatically you remove them from your data analysis, and you carry on analyzing everything else. The double wide dwarfs is it's going to be tricky indeed because it's a lot of noise. So, well, I mean, they get confused altogether.
I mean, I'm not familiar with LISA, but in LIGO you have analogous sources. I mean, in principle, you look for analogous sources which are pulsar rotating, which are monochromatic. And what you do, what helps in detecting, I mean, they've not been detected yet, but what would help in detecting is that they are different locations in the sky. So the Doppler effect is different. So basically, for each, so you pixel the sky, and for each pixel, you have a specific modulation due to the Doppler effect of the Earth, because these sources are still and they are stable. And during the year, there is a Doppler effect, which is different from every direction in the sky. So you can do a sort of match filtering for every pixel, and so pinpoint the source that has exactly the modulation that you would expect for a fixed frequency, but modulated by the motion of the Earth for that direction, and so on. I guess that helps. I mean, that is done in LIGO for monochromatic sources, but the principle, I guess, is the same here.
Yeah, indeed. Okay. So on this population of double wide dwarfs, we injected exoplanets with different distributions, like a similar way we did I showed you before with the other work. And then we tested how many we could retrieve. So in the optimistic case, this is still our galaxy from above. You have that we can detect many brown dwarfs, which are the green dots, and then the red triangles are the circumbinary exoplanet. And this is a zoom in on in the solar neighborhood where you have the Kepler field that I mentioned before. So Kepler was just staring it in one space in the sky, and we detected many exoplanets far away. But yeah, different methods. The colors are just different methods. This might not look that crazy for you, but this is mind-blowing because we haven't detected an exoplanet far away from us. We always just detect it here, okay, apart from the microlensing, but it's just a specific direction towards the Milky Way, the center of the Milky Way. So basically, if we just detect it in here, how do we know that what we see about planets, it's valid for all the other part of the galaxy, right? So gravitational waves are just a really, really cool way that enable us to see far away from us in a chemical region that is like very different from what we are used to in our solar neighborhood. Okay, yes, the limit of electromagnetic horizon is like more or less 3 kiloparsec. Here we are talking about the whole galaxy, so I mean. But even like in the intermediate and in the pessimistic case, we found exoplanets that are far away here, like the red triangles, 3. We had 3 detections, something like that, in the pessimistic case. So that was something that is very, very, very important. This was just to give you an example that the possibility of detecting an exoplanet is mostly a function of the signal to noise of your double wide dwarf. In fact, if you have the signal to noise that is like of 290, when the limit is 7, as I said before, then we can find an exoplanet that has just 0.27 the mass of Jupiter, so a very tiny one. But if we go on lower signal to noise, obviously we go up with the mass because it needs to be more massive for perturbing the center of mass of the double wide dwarfs and hence seeing the reflection in the gravitational waves that we observe. Then you will ask, okay, but this one has like 9063 signal to noise. In that case, it's just a mass of 1099. But this was, which distance? Wait, there was something else. Sorry, there was a reason why I included this. Inclination, mass, separation. I think it was because of the period. I just put like from the different scenario that we had, I just put something that it was very interesting because we were not expecting it. But yeah, the more massive, the better. So that's why we had so many brown dwarfs compared to just exoplanet. Indeed, like if you have a look at the numbers, the brown dwarfs are much more. But qualitatively, this was, again, the dashed lines are the population that we injected, and then what we will be able to detect. So you see that most of the detection for the exoplanets are around high frequency double white dwarfs, so with a period that is very low. The three colors are three different scenarios: optimistic, pessimistic, and negative, right? But also for the brown dwarfs, we saw that we had this injection, and then most of the detection were around higher frequency double white dwarfs. You see that it's difficult to find exoplanets that are below 4 Jupiter masses. In here, there was no effect for the brown dwarfs because they are sufficiently massive to perturb the orbit, perturb the center of mass. No big thing to mention about the inclination. And yeah, this was the last panel where we have the signal to noise of the double white dwarfs. The distance from Earth, so in the optimistic case, which is the blue, we could see them everywhere, basically. But if it was a negative one, we already, there was a specific distance that we could retrieve as a function of, obviously, the signal to noise there. And yes, just to give you an idea of how faint they are, these objects. So imagine that the usual telescope at the moment in the visibles, in the band V, you can detect stuff that is... So for an 8-meter telescope, if you want to observe a star that is like magnitude V13, you need to integrate at least for 3 hours. G and V, they're very similar. I mean, they're very close in the photometric system. And this is centered on G35. So just to give you an idea of how faint they are, these stars. Okay. So the other difference is that, obviously, the more we observe, the longer we observe with LISA, the higher chances we have to detect the modulation of the planet. So this was 4 years compared to 8 years. So you see the difference. This is for the brown dwarfs case. Brown dwarfs are defined as those objects that are not planets, so above the deuterium burning limit, which is 13 Jupiter masses, and the stellar mass, okay? Those are the brown dwarfs. Below, in mass, we are talking about planets. So you see that here we stopped the period, the separation of the object were more or less 8, something, well, more or less for the planet, I think it's 4 or 5. And then if we observe for 8 years, we can go further down in the separation, so we can detect planets that are even further away. Wow, that separation is larger. These are the number in the pessimistic and in optimistic case for both the planets and brown dwarfs. Kilopart. Well, no, separation binary and planet. Yeah. 15 and for planets and 25 for brown dwarfs. Yeah. Yeah, that's a similar plot as before, just as a function of how it changes. Well, the separation, if you do 8 years, you can observe, like you can detect longer well, wider exoplanets on wide orbit. And obviously, the period of the planet is going to increase as well. And the same is for the same effect is for the brown dwarfs. Okay. This was indeed, you can detect it in the Milky Way, but LISA can go and detect the double white dwarfs as well in other galaxies. So here you have a plot of the chirp mass and the orbital period, where these are known galactic gravitational wave sources, both double white dwarfs and cataclysmic variables. And these are, the curves are basically the sky and inclination average signal to noise 7. The way that it was built, it was basically using the noise curves that were accepted by ESA for 4 and 10 years. So 4 is dashed and 10 is solid. And then they average the signal to noise over the inclination angle in the galaxy. And they measure the amplitude of the gravitational wave signal. That is what we need to measure, well, to know if it's detectable or not. And then you see that well, these are just like as a function for the Large Magellanic Cloud, the Small Magellanic Cloud, and Andromeda. So this Andromeda is further away. So of course, like you have a difference between 4 years and 10 years. Yeah. Knowing this, what they did, obviously, it's everything. The signal is a function of the chirp mass of your binary, the frequency of your binary, and your distance, right? So to check whether an object could be detectable, they took like the tiny star that it was on M31, like this one that you see here, which had a chirp mass of 0.9 and a period of 5 minutes. And then they observed it in the plane of distance, which is the other thing that you need to compute the amplitude of your gravitational wave signal, and the orbital period. So this is the famous curve of signal to noise of 7. And basically what you're seeing here, that everything that is like below this curve, you can be detected. So one object with these specific characteristics can be detectable even at the distance of M31. It can be definitely detectable at SMC and LMC, obviously as a function of the orbital period. Everything above cannot be detected. And this is the same thing, but for the distances in the distance and the chirp mass plane. Everything below can be detected with this characteristic. Well, if I put this binary here, that cannot be detected. If I put it here, it can be detected, okay? So this was to have an idea of how many double white dwarfs we could detect as a function of our distance. And these are the histograms, indeed, for the number of detection as a function of the different distances. So all at 10 kiloparsec and 100 kiloparsec for also the chirp mass and the age of the gravitational, and the age, sorry. Obviously, if the further you go, the less detection you have. So what I'm expecting, basically, if I have the same number of double white dwarfs that I have them in the Milky Way, but I put them at that distance, I will be able to detect many less compared to what we have in the Milky Way. So indeed, at the Large Magellanic Cloud, which is 51 kiloparsec, in 4 years I can detect 70 systems, and in 10 years I can detect 150. So we did a test. We took the population, we put at the distance of the Large Magellanic Cloud of double white dwarfs, we injected our exoplanets, and it's the same concept. We can detect them, but they have to be definitely less. The number is smaller, and also they have to be very, very massive. So it has to be more massive than 10 Jupiter masses and have an optimal orbit of the binary to indeed be able to be detected. Okay. We try to see the differences between. Okay, I have. I know that that's a system with with a planet. What happens if I do a Bayesian analysis and I fit for the planet, right? So I know it's there, so I'm going to modulate my gravitational wave, and I will fit for that. So this was one of the simulations for these specific characteristics, and these are the posteriors. So you see in here that is just the ones that are related for the planet, so eccentricity, period, and so on. We see that indeed we are able to retrieve it very well, so the line is passing through the center of the distribution of the true value. So that was good news, right? So our fitting with the third body was working. Exactly the same thing for the brown dwarfs. Actually, it's even better because it's more massive. But then we have an issue in the moment that I don't know that there's a planet there, so I'm just going to fit. Like in the global fit, I'm just going to fit with a general GR model, which accounts for only two bodies. So you'll see here that both in the case for the planet and the brown dwarf, what's happening is like this was the true value, and this was like the retrieved distribution, right? So it's not really matching at all, neither for the brown dwarf case. So and this was the f dot, which is the derivative of the frequency. If you have the derivative of the frequency of your source wrong, it means that you're going to compute completely wrong chirp mass, and it means that you're going to not characterize your system in a good way, which poses a huge, that was before they included the third body fit in the global fit, because we didn't see that until this moment. We're like, oh, what happens if I see actually, if there's a third body, I'm not fitting for the third body. Okay, so different kind of plots, same kind of analysis, where we have undetectable sources for which you cannot really distinguish between a GR template, which is the, the two body, and the third body template. While in here, this was like a f dot and a function of the frequency. While here, we could indeed distinguish them. What we found in this new Bayesian analysis is that basically we were more likely to detect sources for which the period of the planet was half of the period of less than half of the period of the LISA observation. So if LISA observing for 4 years, we are more likely to detect planets that have period of 2 years. If LISA observing for 10 years, we can more likely to detect planets with periods that have less than 5 years. And so on. And this was for the sky localization plane, because obviously, again, you turn on the microphone, but you need to understand where the signal is coming in your sky, right? So this was as a function of the sky localization. Again, undetectable. You don't see much of a difference because more or less they really overlap very well. And in here, you can indeed detect them. Okay, so we have, well, 2 minutes. I'm going to go quickly with that. It was just at the beginning of this project. And we tested, okay, so if we detect with the gravitational wave alone, we can only find we can only determine 3 parameters. But what if we can actually do a follow-up with electromagnetic observation? So this was the parameter space for the planetary mass as a function of distance from the binary. And you have the LISA, the LISA curve, and it was a function of the frequency, indeed. And then all of the other space missions. So you can have an overlap with Ariel that is just observing like below 1 AU, and then direct imaging, which is this curve that is called ICTP-SAIFR. Now it has changed the name of the instrument. I don't remember anymore the new one. Here you have WS first that was covering this, so microlensing will be a good follow-up as well, even if microlensing can happen only once. So that was just to give you an idea that sometimes you need to do this kind of study to know, okay, I can perhaps, if I am observing here with LISA, then which other instrument can follow up this planet? And then you go and check for the other instruments. right, I'm not going to go into detail of that, but if you have GV and then you observe with transit, then you can solve these parameters of the system. If you have GV and direct imaging, then you can solve also these other parameters of the system. If you have microlensing, it's like for all of them, you can solve these ones when you work in synergy with adaptive optics. Otherwise, you can have, oh yeah, the Roman Space Telescope indeed will be very, very good as well. Thanks. And otherwise, like you can have only these in units of Einstein ring and so on. So with astrometry, we can solve for this parameter. And radial velocity, you cannot solve for anything because it's the same concept. Basically, we are detecting it through gravitational wave because it's a Doppler effect, and it's the same thing for the radial velocity. Okay, so that was basically the end. What is good about LISA is that this kind of exoplanet observation are not affected by stellar activity. It can improve, it can test the presence of a population that has never been detected before. So it will be a huge thing whether LISA can detect it. It will be helpful to have more constraints on the final fate of a planetary system because Magrathea is around the old stars that evolved. And we can observe them everywhere in the galaxy and also in the Large Magellanic Clouds. And this was the important thing. If we cannot detect them, then we have really an absolute constraint on the final stage of the planetary evolution. So, because we saw by theory that the method is working and we should be able to detect at least giant planets. If we do not detect it, it means that there's something in the evolution of the planetary system that we are not accounting for which indeed Magrathea planets do not exist. Okay, and that was my final slide for this lecture. Yeah.
So, but I had.
Thanks for the lecture. So the typical localization that you get from LISA, is it good enough that you can actually do the EM follow-up?
Yeah, it's very tricky. It depends by the signal to noise of your white dwarfs, double white dwarfs. If it's a high signal to noise, the error on the sky localization is very tiny, and that helps to point the telescope in that specific place. But obviously, if it covers like a field of view that is much larger than what is covered by any other telescope on Earth, that's going to be difficult. On Earth or in space, of course.
Do you remember some figures like 1 square degree signal to noise ratio of 50? No.
No. That's a work in progress, but we never managed to do the actual computation. Because no. I don't have numbers for that.
So, I mean, that could be a very good PhD project, I mean, or at least, because if it's unknown, that one of the students could do it. I mean, not today, but.
Oh, within this program of LISA, there's so much to do. I have so many ideas and so many things to do, and literally no time for doing it. So, like, very welcome PhD students. I mean.
Okay.
I have another question about the previous lecture when you were talking about observational bias. About the observational bias, and then in this lecture it talks a lot about simulations with like different spectra on the parameters of the exoplanets. Like, do the simulations help in understanding the observational bias? Do the simulations Do the simulations help?
In which context? Sorry, observational bias for what? For circumbinary exoplanets? For detection of circumbinary exoplanets?
Yeah, for the parameter space of exoplanets.
Well, I would say yes, because, like, for instance, the simulation that I did here, well, Gabriele did, I didn't do it, but. Wait. So, yeah, okay, fine. Oh, God. So you see the numbers here, like definitely they are there, but we still haven't detected them, right? Why? Because the double wide dorsal is very faint, right? So ideally that should be there, and we are just not seeing it. It's the same concept for the presence of circumbinary planets around main sequence stars. There's no reason by the simulation that these things are not existing. Well, they are less. Actually, they are more. I'm not sure if you're asking for specific simulation to know whether they could be, or we already know that we are not seeing it because the theory is telling us that they're there.
But like, do the simulations predict like a different mass spectra for the final planet, or like in the terms of the separation to the binary?
So I'm not sure I understand your question, because like the simulation, for instance, is that a priori we are talking about the formation of this object, right? If this object do not form, it means that, okay, we understand why we are not seeing them. But the formation simulations, formation process of this object, they are telling us that they are there. But still. Okay, fine. As I said, they're there, they pile up on the stability limit, which is a function of the separation of the inner binary. If the inner binary is as a separation of, I don't know, 1 year, no, 1 year is too much, but let's just stick with 1 year. It means that they will pile up with a period of 4 to 7 times the inner period, right? So it will be 7 years. To detect something that has 7 years, you will have to observe it for at least 14 years. So we know what's happening, more or less, but we still didn't have time to prove that it's there. So there's an observational bias because we can quicker detect something that has a smaller period. But for longer period, which is the case for these systems, we need to observe for longer time. Before we were just detecting giant planets, well, giant, like Jupiter-like exoplanets. But now with the Bebop survey, radial velocity, that they're observing for 5 years or more, they were managed to go down in mass and detect Saturn-like exoplanets. So the simulation told us like that these objects should be there and have a different kind of mass. It was just a matter of we need more time to observe them. And then it's always an intergame of new observational constraint. You change, modify a bit your model, and then you do the simulation, and then you understand a bit more where to look for, at which angle, and so on. You know? Inclination, sorry, that's what I meant. Mm. Sì. Yeah. Well, it's a matter of how long you're observing. So. Yeah. Mm. Fantastic. No, I mean, I don't know you. So, and their faces, apparently. Okay, good. But we can take a question. No. I was just following the program. If you are telling me that we don't, I'm like, no. I agree with you. Like, I mean, yeah, you had a packed day. Yeah. Okay, we discuss later. Yeah. Okay.